Okay, students, we start here. And the last lecture, we have taken this logarithmic function and exponential functions. Today, we will take the derivatives of both these functions. And so, first, let us start by taking the derivative of exponential function and that of this log function. So first of all, we will take the derivative of e raised to power x, and then we will later on take the derivative of general exponential function, that is a raised to power x. But prior to taking this derivative of a raised to power x, we will take the derivative of log x. So we will take e raised to power x and the derivative of log x. So please do write down derivative of e raised to power x, though it is an exponential function with the value of a being e is a number between 2 and 3. You know it. Now the question is, at the very outset I did tell you that we cannot actually find the derivative of this exponential function and logarithmic function, but unless until we don't know their expansion. See, not only expansion, there is another thing which I will be requesting you that you please be very alert to understand that what is that thing because of which we can't give the mathematical rigorous proof of this e raised to power x. There will be one thing which will be left out therein. So just because of that, we are unable to do it, I will tell you. But prior to it, see, you know that what are the respective expansion of e raised to power x. You know that it is 1 plus x square upon factorial 2 plus x cube upon factorial 3 and so on and so forth. X4 upon factorial 4. Earlier also I did tell you that e is defined as limit n tending to infinity 1 plus 1 by n raised to power n, and therefore e raised to power x will be nothing but this thing, e raised to power x will be what? It will be limit n tending to infinity 1 plus 1 by n raised to power n raised to power x. Now, and this thing we would prefer writing limit n tending to infinity 1 plus 1 by n and x, and then we expand it, and then see, we will see that we get this expansion. But then see, here at this particular stage there are few things which of course are well beyond your syllabus, and that has to do something with the infinite algebra, the reference of which I did give you earlier in my previous lecture on that particular day. What are those things? Please see. Here see, one thing is, I will come to and will explain it to you from this example, because that would be more easier for you to understand it. But just take it for granted that yes, this is the expansion here of e raised to power x. It is an infinite expansion. Okay. So what the thing is, and also you had the knowledge of two limits. One was that limit x times to 0 e raised to power x minus 1 upon x. This is 1, and likewise limit x times to 0 log 1 plus x upon x. This was equal to 1. These two limits you have learned it without giving the proof of actual proof of this thing, that why these limits are equal to 1 and so on and so forth. I will tell you what precisely was the difficulty, that why we are unable to give the exact proof of it, but notionally we did explain it to you. The reason is that e raised to power x, here please see, e raised to power x minus 1 upon x, let us simplify it. It will be, you will say that it is 1 plus x square upon factorial 2 plus x cube upon factorial 3 plus x4 upon factorial 4 plus infinity and then minus 1. You will say that this minus and 1 upon x. You will say that this minus and this minus will cancel and you will be left with x plus x squared upon factorial 2 plus x cube upon factorial 3 plus x4 upon and so forth. And out of all these terms, you say that you will take x common and then you will be left, when you are taking x common, then what you are left with? X upon factorial 2 plus x square upon factorial 3 plus x cube upon factorial 4 plus so on, and this thing will be left out, x will cancel. And when you are taking limit x tends to 0, so what will happen? See, your contention would be that yes, these all elements here, you would be putting x 0, so you will be left only with 1. But actually, see, it is not like that. See, here are infinite terms, and unless and until you don't show that that this series, you will take x common here, I tell you. 1 upon factorial 2 plus x upon factorial 3 plus x square upon factorial 4 plus this thing you will get it. Okay, and this thing and okay, and you close it, so limit x tends to 0. So eventually what it will happen, limit x tends to 0 plus limit of this whole thing, limit x tends to 0 x, and within this bracket 1 upon factorial 3 plus x upon factorial 3 plus x square upon factorial 4 and this will be an infinite series and this way. Then you will say that this is the product of two functions. Okay, so this is limit x tends to 0 x into limit x tends to 0 and this much of thing, 1 upon factorial 2 plus x upon factorial 3 plus x square upon factorial 4 and so on. Now the important question is that here limit x tending to 0, that is 1, and limit x tending to 0 x will be 0. But then see, unless until this is an infinite series, here of course see, had there been finite terms, you could have taken the individual limits of everything. Then of course see, what it would have resulted in. It would have resulted into something 1 upon factorial 2 plus say 0, 0, 0. Please get my point. Here see, there are infinite terms. When you are taking limit of x tending to 0 of this infinite terms, see, you don't know that will it be equal to the individual limit or not. Had there been finite terms, then of course certainly it would have been equal to the sum of the individual limits of each term. And then see, by that virtue, it would have been 1 upon factorial 2, rest all would have been zeros. Because x is 0 in the numerator, you would have kept it. Now, question is that, since there are infinite terms, then we can't say that what will be the limit of this thing. Because there in this particular phenomena, that the limit of the sum of infinite terms equal to the sum of their infinite limits, whether it holds or not, we can't say. So that is the main difficulty, that why we are unable to give the proof of it. But yes, when you will go in your higher classes, you will learn convergence series and divergence series. Now, then see, what we show is that yes, this series converges. Converges means the sum of all these terms will be bounded one, means they can be placed between two numbers, a and b. And once this is there, then of course see, this limit of this thing will be between those two numbers, and that number, those two numbers multiplied by 0 will give, then this whole thing becomes 0. So what is more important is that we need to show that this infinite series is a convergent series. Convergent series simply implies that the sum of these terms, will be between two real numbers, and this is what we really wish to show it. But eventually see, there are ways wherein we can show that this is a convergent series, and that's why limit x tending to 0 x, that is 0, 0 into any finite number becomes 0, and then see, this limit comes 1. So the whole question now revolves around infinite terms. How to get the limit of this thing and the concept of convergence and divergence, which you would be studying in your higher classes. So that is the thing which, because of which right now we are unable to give the correct full mathematical proof of it. So with this understanding, we will accept, yes, that this limit is 1. Likewise, in the case of logarithm also. In the log function also, we encounter the same difficulty. Because logarithmic series, how it is developed, it is nothing. Log 1 plus x, it can be shown to be equal to x minus x square by 2 plus x cube, alternatively plus and minus x4 by 4 plus x5 by 5, and this is again an infinite series. So this is the expansion of this thing. How we get the expansion of this thing, that's another story, because therein again see what we will do. We will employ this thing, the definition of this, we will try to expand 1 plus x raised to power n in 2 ways. See how actually we get the expansion of log 1 plus x is equal to such a thing is that we will take the expansion of 1 plus x raised to power n in 2 particular manner. One method is that it will be limited as 1 plus by the, because n is some say positive number, so which is very large, n tending to infinity. So that in that sense, what it will be 1 plus nx plus nn minus 1 upon factorial 2x square plus nn minus 1 n minus 2 upon factorial 3. I will just give you the x cube plus this thing. My purpose right now won't be this much, and then see what you will do. This function, because you know both exponential and logarithmic functions, they are inverse of each other. So what you will write is that this is nothing but log exponential 1 plus x raised to power n, and this will give you what? Log of e raised to power 1 plus x raised to power 1. No, better you write it like this. Let it be exponential log this thing, because 1 plus x raised to power n can be written like this thing, exponential and log, and they are inverse functions. So this becomes exponential n log 1 plus x, and then see you expand it. So what it will be? 1 plus n log x e raised to power, this whole thing is now x, e raised to power x. In this thing you put this thing, so what it will be? It will be n log x whole square upon factorial 2 plus so on, so forth. Then what we will do, see here, what we will do here is that, see, 1 plus x raised to power n we have written in 2 infinite ways. One is this particular manner, other is this particular manner. Now what we are noticing is that here we are seeing that what is the coefficient of this thing? This thing, n, it is log x, okay, n 1 plus n log x log n this thing, so 1 plus x raised to power n. You want log 1 plus x, okay, so it is log 1 plus x, sorry, here see this expansion you have written somewhat faulty. It should be like this. We see it is not like this. It is 1 plus e raised to power this much of thing. So e raised to power 1 plus x. X is this much. N log 1 plus x upon factorial 1 plus n square log 1 plus x whole square upon factorial 2 and so on. Yes. So these are the two expressions. Number 1, number 2. Now what if we are doing it? That see, we will here in this thing we will collect the coefficient of n. In both the series, what we will do, we will collect the coefficient of this thing. We can write log 1 plus x upon x and x tending to infinity, suppose. So this n will become x, this x square and so on. Now see what we will do. Here the coefficient of x is what? Log 1 plus x. Please see, coefficient of x, in rest of the terms it will be x square, then x cube and so on. So here see now these two are the expansion of the same thing. What that is 1 plus x raised to power n. So what we will do or see better course of you can keep it as n. Please keep it as n. No need of changing it. So see 1 plus x raised to power n. This is first expansion, not this one. And this is the second expansion. In the first expansion, please see what is the let us in this thing let us calculate the coefficient of n. N will be 1. This thing see x. Please see x. Here what it will be? It will be n minus n x square upon factorial 2. So a minus x square by 2. Here n will be 1 into 2 plus and x cube upon factorial 3. So see in this series when you will collect the coefficient of this thing n, so what you will find this particular series, and what you will find the coefficient of this thing n in this series, it will be log 1 plus x. Now see since they are the expression of the same thing, the respective coefficient of n square, n cube in both the expression, they should be same, and as such this is the way how indirectly we calculate this logarithmic expansion of log 1 plus x. So this is another thing which of course we have just given a reference of it, but then let us come back to our main point that yes, how these actually help us in getting the derivative of the thing is that yes, once we accept all these things, that yes, this limit log 1 plus x upon x when limit x tending to 0 is 1 and limit these two limits which I earlier wrote, limit x tends to 0 e raised to power x minus 1 upon x, this is 1. Likewise limit x tends to 0 log 1 plus x upon x, this is also 1. Now here see, as I said, when you will now in the case of the logarithmic series, you will encounter the same difficulty, because y log 1 plus x upon x limit x tends to 0 is 1. When we visit the proof of this, then we will expand log 1 plus x. It is what this limiting part we will keep outside, limit x tending to 0. This series is x minus x square by 2 plus x cube by 3 minus x4 by 4 plus and then minus 1 eventually, and this thing upon 1 by x. So no, it is not minus 1 here. It is only log 1 plus x in this series. Then see, you can take x common and this x will cancel. So what you will get is 1 minus x upon 2 plus x square upon 3 minus x cube upon 4 plus x4 upon 5 and minus 1. Now this is again and 1 by x cancel. You have taken x common from the numerator and that x cancel here, and then this limit x tends to 0. Now one way is that you can say that yes, we will take the individual limits, and this x, this will be 1, this is 0, this is 0, this is 0, this is 0, because 0 upon 4 is 0, 0 upon 5 is 0, and the rest all the things will be 0. But then again I would like to caution you, it is not like that, because this series will contain infinite terms. And then see, if each term is tending towards 0, then you can't say that this entire infinite series will also tend towards 0. That is the main difficulty, that we had to show that this particular series is convergent. Now, in order to show this convergent series, what we do? 1 minus, if you take x common, you will get 1 by 2 plus x by 3 minus x square by 4 plus x cube by 5 and so on. Now limit x tending to 0 will be limit of this thing, and this will be the limit of this portion. This is one portion, this again is the second portion. We had to show that this series is convergent. Because if this series is divergent, then 0, this limit of x being polynomial, this will be 0, and 0 into infinity will be, we can't say what it will turn out to be. But if this series is convergent, then of course it will have a finite sum, and this finite sum into this limit 0 will make the whole thing 0, and then of course we can justify that the limit of log 1 plus x upon x will be 1. So this is the real difficulty which later on you will study in your higher classes. So right now we will accept all these things and we will see that how we can really find the derivative of all these things, making use of this thing. Okay, so I take up now the exercise here. See, students, all these things, of course, you need to know it, because you will find that all these things you will be frequently making use of, and it is better. See, it is not that you need to. Whenever you have the opportunity, you can always come up with the proofs as and when see you get an opportunity to it. But then see, such things should remain in your mind, that yes, why this thing is, why this with all the mathematical rigorousness, we can't give the proof of it. So once we accept this thing, then of course see, we can easily find the derivative. First we find the derivative of exponential at e raised to power x. So what it is by fundamental definition, it will be limit e raised to power x plus h minus e raised to power x upon, or better you write delta x, e x upon delta x, and delta x tends to 0. Delta x tends to 0. We have simply invoked the fundamental definition of this thing. And then what we will do, we will take here, this is, we can write e raised into delta x minus e raised to power x upon delta x, limit delta x tends to 0. This whole thing. And then see, rest of the things are very simple. Here, when we will take e raised to power x common here, and what we will get is e raised to power delta x minus 1 upon delta x, and this thing and this whole thing, and limit delta x tends to 0. Now please see, x is constant, only what is changing is your delta x. So this thing is nothing but limit delta x tends to 0 e raised to power x into limit delta x tends to 0 e raised to power delta x minus 1 upon delta x. Now students, see, you have to be very wise enough, and this needs a little bit of understanding. This is a function of x. Nowhere delta x will be coming. So as a matter of fact, e raised to power x, when delta x tends to 0, under this limit it will be a constant function. Please see, it is just a constant. E raised to power x is just a constant, and as such its limit will be e raised to power x only. Please see, this point needs understanding. Why with respect when delta x, see, in e raised to power x you don't have delta x anywhere, and as such see, this is constant. When under the limit, when delta x tends to 0 e raised to power x you are taking in e, and in e raised to power x nowhere delta x is coming, so it is just like a constant, and you can take it outside and limit 1, so it is nothing but e raised to power x. Please see, it is constant. You have to be careful enough, because under the limiting condition, what is the variable which is changing? Delta x. Delta x is the variable, and this limit is like a raised to power delta x minus 1 upon delta x. What it is 1, and therefore the derivative of e raised to power x is nothing but e raised to power x. See, this is one good example where the rate of change of a function is the function itself. So this is one thing which you need to understand. Let us now take the derivative of log 1 plus x. Please see, all these things, proofs are not in your course, but we are taking it right now just to give you a better in-depth therein for the subject. Now, on the similar grounds, we will take up here the limit of another important function, that is log function. Log function, and then we will take the this thing, limit of general exponential function, that is a raised to power x. Okay. Now we will take the limit of log x function, d by dx of log of x. So what you will do, you will invoke the general general principle of differentiability. Okay, and that demands that this is nothing but limit d by dx log x. It is log, again, x plus delta x minus log of x upon delta x, and this whole thing limit delta x tends to 0. Now here what we will do, log m minus log n is you know what it is, log m by n. So this will fetch you what, limit, this will give you log x plus delta x upon x and minus that's all, log mn upon delta x, limit delta x tends to 0. Please see. Now what it is, when we will open it, we will get this thing to be nothing but limit delta x tends to 0 log of, yes, 1 plus delta x upon x and upon delta x. So now this delta x we will rewrite like this, limit delta x tends to 0. Please see. This is log 1 plus delta x upon delta x upon x, and then we are multiplying by this thing and this whole thing. So 1 upon x. Now we will take this to be one function and this whole entity to be another function. This is the product of two functions. This is the product of two functions. So this is limit delta x tends to 0 1 upon x into limit delta x tends to 0 log of, yes, log of 1 plus delta x upon delta x upon x. Okay. Now when delta x tends to 0, this implies delta x upon x also tends to 0, because here you 0 upon, when see something is between, in a numerator this thing is between small, you divide by something, if it is x is taking greater than value, it will become more smaller, but in case it is something between this thing less than 0 and it like between 0 and 1, then of course see, the value will increase. But then see delta x, it is up to you. You can make it as small as you please, but x has been given one fixed value, because differentiability at a point you will be finding at x, because see here differentiability where at x you are finding, x will be at a certain point. So once you have defined this thing by delta x, you can make it as small as you please. So the point is to say that this delta x upon x will also tend towards 0. Once this tends towards 0, then this whole thing will become 1. Limit log 1 plus x upon 1 plus t upon t is 0, provided t tends to 0. So if we will put delta x upon x is equal to t, so it becomes log 1 plus t upon t, and that's why this is nothing but 1 upon x. So this is how we have found that the derivative of log x is precisely 1 by x. And now with this two important derivatives at our disposal, we are now in a position to find the derivative of this thing, log of a raised to power x, the general, this thing, sorry, the derivative of a raised to power x. We will now try to find the derivative of the general exponential function a raised to power x. Remember that we have initially found the derivative of e raised to power x only. So what we will do, we will make use here that this is nothing but e raised to, we will write it that this is nothing but log, exponential e log a raised to power x. Okay, and this is nothing but d by dx of e log m raised to power n is what, exponential x log a, e raised to power this thing. So it is precisely finding the derivative e raised to power x of log a. The same thing I can do right like this. this way. So now here we will make use of the chain rule formula. Chain rule formula. So it is what? We will put t is equal to x log a. X log a. So it is d by dt of e raised to power t into dt by dx. dt by dx is from here. dt by dx can be calculated to be nothing, but it will be how much? Log of a. This is constant, and d by dx of x, so that is 1. So it is e raised to power t, because derivative earlier we have seen that the derivative of e raised to power t is e raised to power t, and dt by dx is nothing but it is log of a. Let us put the value here. So it is log a, and e raised to power t is nothing but your a raised to power x. What is this? Your t? T is x log a. Exponential x log a. Yes, exponential log a into e raised to power x log a. So what it is again what we can write it, e raised to power log a raised to power x. So this is log a into e log, again exponential log inverse of each other. So what we get is that this is the derivative. And so these are the three important. The general derivative of a raised to power x is simply log of a into a power x. So this is the third derivative. Now based upon all these things, we are now we have done almost all the methods with almost the complete theory, and now we will take the questions here. And my request to all the students would be that please take these questions in the right earnestness and do each and every question good number of times, because see this 5.4 is easy one. Then we will take up the miscellaneous and the parametric function. But today my request would be I am taking you this exercise 5.4, which is a mix of all the questions, and we will quickly take up this exercise 5.4. Good one. Yes, so we are taking the questions from this exercise 5.4. Yeah, first question, differentiate e raised to power, question number 1, it is e raised to power x upon sin x. Its derivative has to be found out, d by dx. So simple, here you are seeing that it is division of two functions, therefore by quotient rule, what it is the denominator is square and denominator sin x into d by dx of e raised to power x minus e first numerator and derivative of the denominator dx cos x. So it is sin x, derivative of e raised to power x is what? Into e raised to power x minus e raised to power x, and derivative of cos x is what? Minus sin x upon this sin x whole square, whether you write or you write sin square x. So this is the answer. Question number 2. Here it is e raised to power sin inverse x. And my request to all my students is that see they should not adopt this shortcut method. Please see, because you are at initial stages, and if you will adopt the shortcut, then you are liable to lose the marks. So question number 2, e raised to power sin inverse x. Okay, suppose y is this thing. So dy by dx is what? It is d by dx of e raised to power sin inverse x. Now this is what? Function of function. What is your inner function? Sin inverse x. So what you will do, that you will put the internal sin inverse x is equal to 2, because in the derivative of the function of function, what the important thing which you have learnt is that first of all we will put the internal function equal to t, and then we will differentiate the external function with respect to internal function, and we will multiply the derivative of internal function with respect to independent variable x. In this case x, but it could be some other also, depending upon the situation. So this thing becomes what? D upon dx of e raised to power t Okay, and therefore by this thing you can what write? V raised to power dt into dt by dx. Okay, and this is what? E raised to power t. Just now you have seen that the derivative of this thing, and dt by dx, where from where you will calculate from here, it is 1 upon under root 1 minus x square. So put this value here, 1 upon under root 1 minus x square, and then here you put the value of t. T is your sine inverse x, and 1 upon under root 1 minus x square. See, I tell you that these all the things, right, clearly. So this is the derivative. Here see, you will have now mix of all the things. At times you will have to make use of this exponential function, at times composite function, at times logarithmic function. So this is all what you have to learn at your class 12 stage. So do it, gain the perfection, and then see, try more questions beyond the book, and for the completion, whatever you feel like. But then this is how you will be proceeding. Now see, still now not you have done any question based on this thing. Now interesting question, all these questions are good one. E raised to power x cube. Again see, question 3. E raised to power x cube. Okay. Again see, it is a function of function. Now see, you what for the students, they have to be smart enough to know where what is the function of function and what are the things. Here see, in e raised to power x cube. Please see, what is the internal function? X cube. And what is the external function? Your exponential function. So what the thing is, if y is equal to this thing, then dy by dx will be equal to e raised to power t d by dx. Now at times see, please keep it, and you put internal function t is equal to x cube. See, here see, good students, they will write internal function t. And others see, who will be simply cramming the formula, they will say yes, put t is equal to x cube. But when you write internal function t, then see, it means you know the things perfectly. So now, with this understanding, so what you will do, this derivative, first you will differentiate the external function with respect to internal function and dt by dx. Yes, for remembrance it's important. It's another thing that when it is seen, when after you have made a substitution that interpolated t, then see this d by dx, then mind it that here you first differentiate with t and then t by this with respect to x. But it is not like that delta t is cancelling. This particular aspect we have already explained you earlier. But today again I am explaining you, it is not that they will cancel here. It is just because this formula for derivative of the composite functions has been attained this thing, by virtue of that we are writing like this. So it is, otherwise this is a notation, d by dx is a notation. Okay, so it is e raised to power t and dt by dx. From here it is simple, dt by dx is 3x square. So you can put the value here at place of this thing and then put the value of t here. T is your what? X cube. And e raised to power x cube, 3x square, that is the answer. So questions are very easy. But see, if you have crammed the things, then of course see, you will get confused. Now see, till these three questions, what we have tried was this thing, sine tan inverse. Now see, I will take a sine tan inverse e raised to power x, e raised to power minus x, e raised to power minus x. This is your question number 4. Now again, here it is the composition of three functions, the innermost being e raised to power minus x, the middle one being tan inverse x, and the outermost being the sine inverse x. So when you have two or more, composition of two or more functions, then what is the strategy? The entire lot, barring the outermost, you take it to be t. Assume it that to be the internal function, because you need to visualize this composition of 3 or 4 or more than 4 or whatever, 5, 6, whatever the function is, that entire lot, barring the external most one, that is in this case sine. So what is to be kept as p? P is equal to tan inverse e raised to power minus x. That this entire part. This is the composition of two functions. So this has to be first sine t, and so dy by dx will be what? D upon dx of this thing, and this is what? D upon dt, because now we are taking this entire lot to be the internal function, that is, which itself is the composition of function. So we will invoke this derivative of composition twice, because as you know it is d upon dt sine t and dt by dx. Okay, now for obtaining dt by dx, what we will do? It is again the composition of two functions. So what we will do? We will put e raised to power p is equal to what? E raised to power minus x. So it is p is equal to tan inverse p, tan inverse p, and then dt by dp will be equal to yes, d by dp tan inverse, okay, sorry, dt by dx, because you have to determine the value of dt by dx. So it will be d by dx of tan inverse p, which will be equal to, I will write here, d upon dp of tan inverse p into dp by dx. So tan inverse p is what? You know, it is 1 plus p square, and dp by dx you will here. In fact, this is again a function of two functions. Here it is not e to power x, it is minus x. So minus x again you will put equal to, say, q. So it is dp by e to power q. So dp by dx, please see, dp by dx will be equal to d upon d x of e to power q, which can be written to be d upon dq e to power q into dq upon dx, and dq upon dx here, from here it will be what? Minus 1. So it will be equal to how much? E to power q. Derivative of e to power q is what? E to with respect to q, e to power q, and this is what? Minus 1. Put the value of q. Q is how much? Minus x, so it is e to power x and then minus sign. So, and therefore the value of dp by dx from here you can put it to be what? Minus e to power minus x. Okay, and then put the value of p. P is what? P you have taken to be how much? Yes, p is this thing, p is e to power minus x. So 1 plus e to power minus x, and p square is this thing, and then minus e to power minus x. This is what is your dt by dx, whose value you need to substitute over here. Now d by dt of sine t is what? Cos of t, and dt by dx from here, it is minus e raised to power minus x upon 1 plus e raised to power minus x whole square. This much I think. Put the value of t here. T is here tan inverse e raised to power minus x. So cos tan inverse e raised to power minus x, and then into minus e raised to power minus x upon 1 plus e to power minus x whole square. So this is what is to be done here, students, and still not you have taken any question on logarithmic series. Yes, the fifth question, of course, now that's based on this thing. We will take the fifth question here, and then we will proceed further. Yes, fifth question, question number 5 here of exercise 5. This is the important question 5. Log of cos ex, cos of e raised to power x. Yes. Again, see, you won't be applying this logarithmic function. It is again a function of function. So what you will do again? Three functions. It is the composition of three functions. Innermost being exponential function, intermediate one being cos x, and the outermost being log x. So what the thing is that this entire, you will put t is equal to cos of e raised to power x is equal to t. So this y is equal to log of t. Log of t. So dy by dx will be equal to what? And please write in full. D upon dx of log of t because students they write d by dt of log of t and then dt by dx. dt by dx. And this is what? D by dt log t is 1 upon t and then dt by dx. Let us find the value of dt by dx. This is your t. So this is again a function of function. So what you will do, here you will put p is equal to e raised to power x. Because in the composition of the function, internal function has to be kept equal to some variable, and then this is dt by dx. You will differentiate with respect to d by dx of cos of p, and this will give you what? D by dp of cos of p into dp by dx. dp by dx from here it is nothing but e raised to power x, and therefore cos p is what? Minus sin p, and dp by dx is what? E raised to power x. This value you have to substitute here. So 1 upon t. T is what? Cos ex. So you put cos e raised to power x, and at place of dt what you will put? Minus sin p into e raised to power x, and then put the value of this thing p. It is minus sin p is what? E to power x into e to power x. So this will be the way out. This is how you would be doing. Certain students, if they will adopt the shortcut method, see that will amount that you are cramming the things, and even in the board examination you will be losing your marks. And please remember, it is of vital interest that in each step you need to understand that what is the justification behind each and every step. So this is how you will be taking up this question number 5. Now this question number 6. Yes, question number 6. Of course, see, we are doing it. It is and then please don't try to do your question without seeing the answers. You should try it at your own level. Okay. Question number 6. Good one. See here, the questions are good ones. I request all of you to do it. It is e raised to power x plus e raised to power x square plus e raised to power x square plus e raised to power x cube plus e raised to power x4 plus e raised to power x5. Now, simple here. This is your function y. This is x. This is e. Now, one way is, yes, dy by dx, what it would be? It would be d by dx of e raised to power x plus d by dx of e raised to power x square plus d by dx of e raised to power x cube plus d by dx of e raised to power x4 plus d by dx of e raised to power x5. Now, what you need to do is, please see, here one way is you can show that d by dx of e raised to power x n is equal to how much? N e raised to power x to power n. How? Please see, e raised to power n x raised to power n minus 1 and e raised to power xn. This is what we will show it to you. How? A general proof. D by dx of e raised to power x to power n is some integer, n is the element of some n. Let us see what it is. So d by dx of what it will be? E raised to power t, and t is what? X raised to power n. So it is d by dt of e raised to power dt into dt by dx. And this dt by dx from here you can calculate, it is simply nx raised to power n minus 1, general formula. So it is e raised to power t into nx raised to power n minus 1. And put the value of t back here, e raised to power x into nx raised to power n minus 1. Once you have obtained this formula, then of course directly you can put the values here in. So this is the formula, and based on this thing, you can put the values here. E raised to power x is e raised to power x. E raised to power x is square. Put any is this thing 2 here. So 2 x raised to power 2 minus 1. 2 minus 1 into e raised to power x square plus ex cube. It is 3x raised to power 3 minus 1 x cube plus likewise 4. You can make use of this thing. X raised to power 4 minus 1 x e power how much? It is n minus 1. So it will be square here, it will be x square x cube and likewise 5 x to the power 4 e to the power x to the power 5. So this is how you can get the answer. I stop it here with the request that you will do the remaining questions and we will take still see the question based on the properties of logarithm. We have not done it, but as it is in the next exercise, so we will take those questions therein. Now with the request that you will take the exercises on your own without seeing any help book or etc. Thank you.